agenda that I just discussed. So yeah, let's just go to the poll. Should
Carrie,
we
is it
skip
possible
polls?
for you to bring up the poll?
Yep, let me do that. Should be seeing the poll.
Okay, great. So our first poll question is, in 2018, what percentage of MISO system peak demand is equal to peak demand savings from demand response, where system peak demand was 123 gigawatts? So 10%, 7%, 2%, or less than 1%. So most of you got it right. The correct answer was C, 2%. Peak demand savings from demand response were equal to 2% in 2018, with about 1 gigawatt from both residential and the industrial sector, and half a gigawatt from commercial. So next slide. So let's start by, go up one, please, Carrie. Perfect, thank you. Let's start by defining net load shapes. So generally, net load shapes are defined as the profile of a customer's grid electricity demand over time as affected by behind-the-meter generation and other DER technologies. So while net load can refer to the total electric demand in the system, minus wind and solar generation, in this context, we're discussing net load of smaller aggregations of individual buildings, such as that observed by a neighborhood or at a feeder level. The importance of these aggregate net load shapes is that once you combine individual net load shape patterns, you begin to see characteristic shapes as a result of shared building consumption patterns. This allows the utility to better target desired impacts using DERs and understand what their impact could be on a particular net load shape. Next slide. And furthermore, the opportunity and need for net load management using distributed energy resources only continues to grow as variable renewable energy, such as solar, is further adopted. So even at low VRE levels, DERs provide an opportunity to control electricity load during periods of high system cost, such as the left side of the energy price duration curve shown here, where a small proportion of hours have exponentially increasing costs. And with more VREs, which can also be DERs, you have an even greater distribution of prices, both for the entire year and throughout a single day, which is shown at in that bottom figure. This provides even more opportunity to shift load to periods with lower prices, such as with demand response, or use storage to dispatch VRE generation into higher price hours. Next slide. So go 2 down. Right there, perfect. And net load shapes are changing with increasing distributed solar. As shown by the top right figure, small-scale solar has more than tripled over the last 5 years and is projected to grow more as capital costs decrease within the US. As the bottom right figure shows, distributed solar adoption is not currently high in MISO, but emerging regulatory goals at the state, city, and utility level indicate that may change. As these organizations work towards decarbonization goals, solar penetration will inevitably increase. So next slide. So when thinking about the impact of DERs on net load, it's helpful to place their impact into a few different categories. And so the way we categorize that here is generation, such as distributed solar with or without batteries, energy efficiency, which provides ongoing reduction in energy use, load shifting through demand response and storage, which changes the timing of electricity use, load shedding, which reduces electricity use for a short time and typically on short notice. So shedding is typically dispatched during peak demand periods and emergencies, which is the way to think about that. And then we think about how these strategies work together to improve the net load curve overall. And so the graph on bottom, which I believe was discussed a little bit 2 days ago, kind of shows the different ways that those different impacts can actually affect the net load. So let's just go to the next slide. So now I'm going to present a few illustrative examples that demonstrate the different ways that DERs impact net loads. We'll cover solar, solar plus storage, standalone storage, efficiency, and demand response separately, and then I'll discuss the impacts of combining them. Next slide. So starting with solar, the primary impact of distributed solar PV is lowering building net load through self-consumption and net export. Self-consumption offsets customer consumption from the grid through on-site generation, but once the site's net load reaches zero while solar is generating electricity, excess solar PV is exported to the grid. The figure here shows the increasing impact of adding solar to individual homes. While some homes with solar are exporting during midday, even during those low penetrations, it becomes evident as higher penetrations reveal a negative aggregate net load. And while I showed earlier that MISO solar adoption is low, the bottom right figure shows how shapes for other locations are beginning to appear in locations with high penetrations, such as Oahu, where 90% of installed solar was distributed as of 2014. While solar generation is not directly controllable, besides through curtailment, utilities can proactively manage its impact on net load in a few different ways. And some examples of that here are using late in day time of use peak periods to promote west-facing solar, thereby shifting its peak production time, changing solar compensation to promote different sizing of installations, establishing time of use rates that promote shifting of consumption to periods of higher solar generation, and promoting other technologies that smooth the midday curve, such as dispatch using energy storage, which I'll discuss next. So next slide. So when customers install solar and storage together, the midday peak can be reduced by shifting solar generation through storage to other periods when storage is financially incentivized to do so. Energy storage dispatch can be economic for a few reasons. Two primary reasons being, one, scenarios where exporting solar is less valuable than shifting generation to other periods with positive net load, and the second being scenarios where time of use pricing enables the system to achieve higher value by offsetting positive net load in periods with higher electricity prices. I should also say that here we refer to time of use rates as period-based pricing, where they vary based on time and day of week as well as season. So we're showing both cases separately in the figures on the right, where the top figure promotes energy storage dispatch through time of use pricing, and the bottom figure promotes dispatch through a lower solar export rate compared to the flat retail rate. So seen in the top figure, the time of use rate ultimately smooths the midday peak by charging solar to storage and then discharging only during the peak period. This creates a more significant net load reduction during the peak period, as observed in the sudden load shift at 5 p.m. In contrast, the lower export rate in the bottom figure demonstrates a value of solar tariff, which is an export rate for solar that is separate from the retail rate customers pay for electricity. In this case, the value of solar tariff enables storage dispatch to always be more economic than PV export. What this ultimately leads to, first, is even more charging of storage from solar than in the time of use case, thus more midday net load smoothing, and the second, storage dispatching into all periods where there's positive net load. Next slide. And so what those previous cases show is that utilities can design rate structures that promote effective dispatch of energy storage, because energy storage behavior is quite sensitive to electricity price and rate schedule, as well as efficiency losses, among other technical parameters. So here we're showing a comparison of summer and winter behavior for an aggregation of 60 buildings with time of use pricing and net energy metering 2.0 in order to demonstrate other ways energy storage might behave. In cases where time of use pricing has a very low peak period, storage may actually be more economic to utilize grid charging instead of charging from solar at all, as shown in the top figure. This can even cause new net load peaks to form, which you can see here. Furthermore, solar generation is not displaced at all, despite the presence of storage. But otherwise, the use of time of use pricing does not always promote storage dispatch. So for example, in the bottom figure, there is still time of use pricing, like in the summer case, but the difference in time of use pricing is too small and the incentive to dispatch is eliminated. So although the price differential is positive, storage must overcome round-trip efficiency losses in order to provide value through dispatch. What this ultimately implies is that rate design can be used to promote favorable storage dispatch for managing net loads, but it needs to also enable economic dispatch for building system in order to be effective. Next slide. So what we've been discussing is how storage behavior is affected by volumetric electricity prices, meaning electricity charged by dollars per kilowatt hour. So let's go to the next slide. And so now what we're talking about is standalone storage, which is also being adopted by large commercial customers to minimize demand charges, meaning electricity is charged by dollars per kilowatt of electricity instead of by kilowatt hour. So in this case, when building demand is low, standalone storage charges using grid electricity. Then, when building demand is high, storage discharges in order to shave peak load. Since the goal of this type of dispatch is to reduce the customer's electricity bill, the time of discharge is dependent on when demand charges are high. So in this figure, you can see what this looks like in two common cases. So we have one case where customers are charged by non-coincident demand, meaning the time of building demand does not matter. And then in the second case, customers are charged by time of use demand, meaning the certain period of demand have higher costs. So for non-coincident demand charges, storage dispatches throughout the entire time of high building demand, causing a uniform peak shaving. However, with the time of use demand charges, which is that peak period range you see, storage only dispatches during the peak period. Since the storage system has a fixed amount of energy, the discharge during the peak is much deeper than with the non-coincident demand charges. But because storage waits to discharge until the peak, a large ramp occurs between the peak period and all other hours. So both of these structures have net load impacts that could be desired by utility, but their impacts certainly are not the same. So let's go to the next slide to kind of summarize storage. So now we've seen a few ways utilities can use energy storage to manage net loads. To highlight a few important takeaways, pairing storage with solar can help smooth midday net load and provide net load reduction during other periods. Standalone storage can accomplish this too, although grid charging can create new peaks. Regardless, rate structures need to incentivize economic dispatch, but utilities can use this to target when and how storage dispatches to maximize desired impact. And this could also include utilizing value of solar tariffs to promote higher self-consumption and less solar export. Okay, now that we've covered storage, let's go to a poll question before discussing energy efficiency. So in 2018, what percentage of incremental energy efficiency peak demand savings were from the residential sector? And the total peak demand savings from energy efficiency was 1 gigawatt. Okay, great. So most of you said 15%. The correct answer is 42%. So 42% of incremental energy efficiency peak demand savings were from the residential sector, with a majority of the other savings from commercial and a small amount from industrial. So we'll talk about why that's important next. So let's go to the next slide. Thanks. Or let's go down to energy efficiency. Perfect. So energy efficiency measures impact net load without active management. And while we historically think of energy efficiency as providing overall demand reduction, the timing is also important for net load management, such as targeting peak demand periods. So energy efficiency programs are used to upgrade common equipment in buildings, but different upgrades affect different time and seasonal periods of net load. For example, cooling will impact summer peak, while heating will impact winter peak, whereas other programs will reduce net load throughout the year. What's attractive about energy efficiency is that utilities can utilize this diversity of measures to strategically design programs to target reduction by period, season, and customer sector. Next slide. And so moving on to the first demand response strategy, time of use pricing provides net load management opportunities through customer responsiveness to price signals. So even without enabling technologies such as solar and storage, utility pilots have shown that customers consistently reduce or shift peak period consumption with time of use pricing. This was shown to be true for both opt-in and default options in multiple studies, but it also showed high retention rates in both cases. So for example, the figures on right show modeled net load based on customer response that was measured for a San Diego Gas and Electric pilot. An important takeaway here is that we're showing a time of use case that has 3 price periods. And those pilots show that in those cases, customers increased consumption during the off-peak, super off-peak slightly, but reduced their consumption during the peak. However, in time of use cases with a 2 price period, customers still reduced their peak period consumption while showing near 0 additional consumption during the off-peak. So let's go to the next slide. So in comparison to time of use, critical peak pricing provides more utility control by signaling peak days, which results in additional customer load reduction. So critical peak pricing works by charging customers a higher price for energy during a predefined period on critical event days, which are called infrequently throughout the year, typically 5 to 22 days depending on the program. For example, enrolled customers may receive a day-ahead notification, meaning the price they pay for energy the next day will include a much higher CPP period only on that following day. And they're incentivized to enroll through this slight price reduction for all other times, or rather they are incentivized to enroll because they receive a slight price reduction for all other times throughout the year. CPP prices are much higher than time of use prices, which where some of the lowest CPP prices are 4 times that of the off-peak rate, which ultimately incentivizes customers to have even more reduction. The figure here shows the modeled impact of CPP based on the percentage of customers enrolled, and a peak day is being shown because event days are called based on particularly high expected demand. So this is important because CPP enables utilities to manage net load during peak days at a deeper level than time of use. By applying an even higher price signal on those days, customers respond with additional net load reduction. Okay, so let's go to the final example of demand response on the next slide. Direct load control provides an additional layer of utility control by using load control instead of customer price responsiveness to reduce demand on peak days. With direct load control, or DLC, enrolled customers allow utilities to remotely cycle air conditioners and water heaters, as well as adjust thermostat settings during event days for pre-established periods. During events, equipment is cycled between 50 to 100%, or thermostats are adjusted by a few degrees to cause less HVAC usage. Like CPP, event days are infrequent and customers receive an annual credit for enrollment. The advantage of DLC is that it directly targets equipment responsible for driving that peak demand. And by controlling it directly, the utility can better estimate the net load impact. So the bottom figure actually shows the top 10 utilities in MISO with the highest enrollment, as reported by EIA, where many co-ops already have high enrollment of DLC programs. And so there are additional demand response programs besides the 3 I've just shown. I think there's a table for that on the CPP slide. But these provide an idea of how demand response can be used to impact net load on a distributed level. So let's go to the next slide. So by combining DERs, utilities gain a menu of options for managing net load through generation, shift, and shed. So this is enabled by DERs acting in concert, and certain scenarios show how DER behavior is enhanced by the presence of other DERs. So for example, the figure on right shows different aggregate net loads for a peak summer day with time of use pricing where 100% DER customer adoption is assumed, but with different DERs actually applied. And so what I want to particularly draw your eyes to here in these figures is the comparison of the case that has CPP, PV, and storage compared to the case that just has PV and storage. And what this is showing is that by the additional price signal from CPP, the storage actually behaves a little bit differently. Whereas without the CPP price signal, storage would have dispatched only during the peak period from 5 p.m. to 8 p.m. With CPP, storage actually starts to dispatch as soon as there's any positive net load, which is at 3 p.m. And what that does is storage actually starts to aid CPP in reducing peak demand. And while this figure is only one illustrative case, it demonstrates how DERs can impact net load simultaneously in different ways that can, in some cases, enable each other. So let's go to the next slide. Looking forward, utilities are beginning to design platforms that tap into DER flexibility through heightened visibility and control over DERs. A great example of this is in California, where state regulatory design is enabling a platform-ready grid. So in California, Rule 21 requires all distributed solar to use inverters with remote communication and grid service capabilities. And while platforms are still developing in California, this allows distributed solar PV installations to be pretty much platform ready so that utilities can control them without requiring additional technological upgrades. Additionally, there was a bill passed in 2019 in California that will foster higher adoption of demand response ready appliances by effectively incentivizing smarter appliances to be adopted in customers' homes. So these regulations enable technologies that will ultimately provide utilities with more visibility and control. On the utility side, some utilities are creating centralized platforms for aggregating dispatchable DERs to control net load, such as virtual power plants that can potentially operate DERs synchronously, provide grid services, and participate in wholesale markets. So kind of like how we talked about direct load control, VPP would enable utilities to schedule and dispatch other DERs, such as energy storage systems. And furthermore, they can aggregate these smaller resources, such as small storage systems in residential homes or even commercial, which facilitate sort of a unified approach to providing demand response and other grid functions for greater impact. And so I've provided some examples of utilities that are testing VPPs through pilots here, and there are a few links there. And then on the next slide, we can go to, I've provided some more questions that states can ask. And then on the following slide, I've provided some references that are useful context for what I've just presented here. So with that, I will hand it over to Matt. Thank you.
Thanks, Chandler. So hi, everyone. I'm Matt Leach from the National Renewable Energy Lab, and today I'll be talking about integrating load shape analysis into grid modeling. Next slide. So there are three main objectives that I want to cover. The first step in estimating the demand flexibility that buildings can provide to the grid is to understand building energy consumption at scale. And by that, I mean capturing realistic building load profiles and variability in energy use across and within different building types. Next, perturbation of control set points, either random or corresponding to specific flexibility dispatch scenarios, such as load shed or load shift events, can be used to characterize flexibility potential by building type and end use. And finally, grid models can be employed to optimize the dispatch of the available flexibility or to quantify the net impacts of specific dispatch strategies. Next slide. Okay, so what are the key takeaways of this presentation? First and foremost is that demand flexibility should be treated on par with supply side options, so the associated grid impacts and benefits, including operating cost reductions, can be quantified and monetized. And second, DOE and the national labs, including NREL, are developing new tools and analytics to account for the full economic impact of demand flexibility, variability in value based on time and location, impact of distribution system savings on transmission and generation system value, variability in value due to interactions between DERs and between DERs and other system resources, and life cycle analysis for demand flexibility. Next slide. So you've probably seen some of this information in other presentations, but it's important to keep in mind the benefits associated with developing programs around the potential for buildings to provide demand flexibility. Some of those benefits include reduced grid congestion, especially during peak demand periods, reduced energy bills driven by reduced infrastructure costs, minimizing curtailment of renewable generation, and enabling lower electricity costs by reducing grid operating costs. Next slide. So as I touched on previously, understanding building energy consumption is the foundation to any estimation or utilization of building demand flexibility. So first, we need to understand where energy is used across the US building stock, where geographically, in what building types, what end uses, and at what times. Next, we need to understand how those buildings can provide service to the grid. What is the role of efficiency in providing that service? What is the capacity for load shaping? And what are the time, location, and configuration dependencies? Once we can answer these questions, we will have the necessary foundation for demand flexibility estimations and dispatch strategies. Next slide. To answer these questions and to package those answers into powerful and flexible analysis tools, NREL has developed ResStock and ComStock, which are bottom-up engineering models of the US building stock. ResStock covers the residential stock and ComStock covers the commercial stock. These tools have been developed to achieve a balance between speed and complexity. They are highly granular to capture diversity across and within building types. They are calibrated to real data at the sub-hourly level. They can model controls and demand response strategies. They enable scenario analysis for both efficiency and demand response and account for interactions between potential measures. And they provide visualizations for slicing and analyzing data. Next slide. The next few slides provide a brief introduction to the ResStock and ComStock tools. At their most basic, these tools combine a database of building stock characteristics with physics-based modeling and high-performance computing workflows. Next slide. They are built on databases made up of large public and private data sets. In total, there are over 6,000 probability distributions for more than 100 parameters organized in a complex dependency tree. On the right side of the slide here, you see an example of how these parameters are nested. You can see for a particular building type, there are distributions associated with vintage, floor area, and footprint, where each distribution is tied to the selection from the last. Next slide. The models themselves are built up using the DOE tools OpenStudio and Energy Plus, and they enable detailed sub-hourly energy simulations with breakdowns by end use. Next slide. And all this granularity and detail requires significant computational power. To model the full residential and commercial stock requires about 800,000 annual energy simulations. To facilitate this, ResStock and ComStock are designed to leverage supercomputing resources, including Amazon Web Services, and are built around a big data technology stack. Next slide. As ResStock and ComStock are bottom-up models, calibration is critical to ensure accuracy at scale. This is where the end-use load profiles project comes in. For these tools, ResStock and ComStock, there are different scales of analysis and also different scales of data collection and calibration. And while it is important to have parameter distributions that map to the national scale, it's not possible to collect highly granular characteristic data in every region, and even if we could do that, it would not be practical to calibrate to all those data. Next slide. In light of those constraints, the end-use load profiles calibration approach is defined as follows. First, compare results to widely available data, including EIA annual electricity sales data, for example. Second, study regional transferability of non-weather dependent end uses to find opportunity for extrapolation of specific calibration exercises. And finally, perform enhanced calibration for 5 specific regions for which we have AMI data and consumer metadata, and then extend those results to the extent possible. And the bottom line underlying all this work is the guiding principle that model inputs will only be changed when supported by data. Next slide. This slide summarizes the types of calibration data being collected and the source of those data. I won't go into detail here, but you can see the main types of data are utility sales, aggregate load shapes, AMI data paired with characteristic metadata, and submeter data. And the sources of these data are extensive and range from public to private. Next slide. I think we'll answer the poll question now. So the question is, in my state, demand flexibility is considered for use in select all that apply. Achieving energy, demand, or air pollutant reduction goals, achieving a renewable energy goal, integrated resource planning process, distribution system planning process, or shaping energy efficiency or demand response programs. Okay, it looks like the most popular answers were shaping energy efficiency or demand response programs, integrated resource planning process, and achieving energy demand or air pollutant reduction goals. Okay, next slide. So I've talked about, oh, back one, please. I've talked about how Revstock and Comstock can be used to create building portfolios that can then be simulated to generate aggregate load profiles to capture various scenarios. And in the context of demand flexibility, these tools can be used to explore how different packages of efficiency and demand response measures can be used to characterize the demand flexibility potential of specific combinations of region, building type, and end use. So next I want to talk about how the resulting demand flexibility estimates can be packaged as inputs for grid modeling analysis and how that can be useful. And you'll notice that, oh, sorry, go back to this previous slide, thanks. You'll notice that the following discussion is based on analysis that we've done at the bulk power scale, but the concepts demonstrated here apply to the distribution scale as well. And it's important to note also that there are multiple ways to incorporate building demand flexibility into grid modeling. The most sophisticated approach is to represent demand flexibility using a virtual battery or virtual storage and generation model with time-dependent storage capacity and charge and discharge rates. In this scenario, which is presented here and in subsequent slides, flexibility is dispatched by the grid model along with supply-side generation in an optimal way to minimize overall system cost. This enables us to measure the maximum value of the resource and accounts for dynamic interaction between flexibility and generation. A simplified approach could be to optimize dispatch using price data generated by the grid model and then feed the net load impact of that optimization back to the grid model to evaluate the resulting change in operating costs. This simplifies the inputs to the grid model, but assumes that flexibility dispatch won't substantially impact electricity costs. An even more simplified approach would be to skip optimization altogether and simply apply discrete demand response scenarios to the building stock models to determine the net load impact and then feed the corresponding net load shape back into the grid model. Next slide. This slide shows how all these parts and pieces can be combined into an iterative, self-validating workflow. First, starting in the lower left, Revstock and Comstock are used to generate building portfolios and perturb those portfolios to characterize demand flexibility potential. Next, surrogate modeling and aggregation methodology are applied to develop virtual generation and storage models for flexibility by end use. Those models are then fed into grid modeling analysis that optimizes their dispatch, and the resulting dispatch signals can then be fed back into the building portfolio models to close the loop by verifying the extent to which the intended dispatch can be achieved. Next slide. The last thing I want to talk about is how demand flexibility resources can be categorized and how those categories map to specific aggregate model representations. Currently, we group demand flexibility resources into 4 categories: schedulable resources, high thermal capacity storage resources, standard storage resources, and sheddable resources. Each of these resource types has unique characteristics that shape how it can provide service to the grid. Schedulable resources are those that can be moved throughout the day without resulting in a reduction or loss of service. These typically have little or no environmental coupling. An example would be pumping for an irrigation system. High thermal capacity storage resources are typically set point driven and exhibit moderate environmental coupling. An example would be a refrigerated warehouse where you would have a very high thermal capacity and likely be able to float for some time to provide a load shed or load shift. A standard storage resource is similar, but of lower capacity and typically more strongly coupled to its environment. Examples of this would be space heating or cooling. And sheddable resources are those that can be turned off, but doing so is tied to a direct reduction or loss of service. Examples would be lighting or ventilation. The unique characteristics of each of these resource types map to different configurations and parameter definitions for their respective virtual storage and generation models. The remaining slides go into detail on how these resources can be modeled as aggregate inputs for grid modeling analysis. I included them here for completeness, but we'll just touch on them briefly in the interest of time. Next slide. So here we see agricultural pumping as an example of a sheddable resource. In the plots on the right, the magnitude of the resource is presented according to energy service, either energy, contingency, or regulation, and availability can vary by season and also by hour of the day. And in this particular case, you can see that the magnitude of the resource is highest in the summer and spring, as you would expect, and significantly lower in autumn and 0 in the winter. And you can also see that the magnitude of the resource is the same across all grid services in this case. Next slide. So here we see commercial heating as an example of a storage resource. In this case, the magnitude of the resource is highest during winter months when heating is needed and close to 0 in the summer. You can also see that availability dips during morning hours when heating is needed to bring space temperature up to occupied set point. It's also worth noting here that this type of resource can provide the highest benefit to the energy market, down to almost no benefit to the regulation market. And this is because the time response associated with passive thermal energy storage is relatively slow. Next slide. And last, we see commercial ventilation as an example of a sheddable resource. The magnitude of service it can provide to the energy market is 0 in all cases because its generation is restricted to 0. And this is because the dispatch of the resource corresponds to an absolute loss in service. And as such, we assume that it would only be used to provide contingency service for only a very small number of hours per year. Next. So thank you very much for your time, everyone. If you have any questions about the tools and workflows we're developing at NREL and how you can leverage them, please don't hesitate to reach out to me. Thanks again.
Thanks, Matt.